What's up, everybody? Welcome back. Today we are working on my virtual GPU, and today's goal is executing OpenGL shaders. So for context, I thought at some point it would be fun if we could like make a graphics card, right? But the problem is that we don't really understand what a GPU does. And I mean, like, that's kind of a strong statement. We kind of understand that like GPUs can do like lots of floating point operations really fast, kind of in parallel, right? We understand that you plug in a monitor to the GPU and you draw stuff, and that somehow ends up on the monitor. But really, like the specifics are kind of fuzzy to me, right? And so what we are doing is we are tackling that problem of us not understanding everything by just implementing the entire graphics stack in software, right? So the idea here is that if we implement the entire graphics stack, including like a PCI device in a virtual machine that emulates a graphics card, then we will understand what we would need to do if we were to make a graphics card ourselves. And so we've gotten to the point where we can show some stuff on the screen. Let's show our little demo app. So our little demo app is really straightforward. This is an OpenGL application calling GL clear in a loop. It is like doing all of the setup that needs to be done in order to like take a texture, put it like bind it to in a way where the GPU knows that it wants to be displaying that to the monitor. The GPU is then iterating all of the pixels in this texture and setting them to whatever color we set with GL clear. Which means that we've had to implement like all sorts of stuff in like all of the Mesa project, Linux kernel, and as well as like a QEMU device drive, like a device implementation for this thing, right? What we want to do is we want this thing to work correctly. So our application also is supposed to draw a triangle here. I didn't really put it in the middle of the screen because I forgot that it was over here. But I think that it was just like some sort of like, coordinate normalization problem, whatever. But here is a triangle, and this is running the same application on a existing GPU, the VirtIO GPU GL PCI device. And so today's goal is just do the same thing. Now the question is why are we not drawing the triangle? Well, today's modern GPUs are kind of based around this concept of shaders. And shader is kind of like a bit of a funny word, in my opinion. Shader kind of just means like program that runs on GPU. So like the flow of like your typical OpenGL app is that like, say you have like a cube, right? You want to draw a cube on the screen, right? Awful cube, but whatever. Now this cube is going to have vertices, right? So we're going to have like, points in 3D space that mark corners, essentially, right? And the way that this thing is typically drawn is you kind of like split this thing up into triangles, and you ask the GPU to draw each of these triangles individually, hand wavy, right? And some of these edges will overlap, but that's okay because they happen to like they'll be in the same spots. Let's see. Now, if you want to like put this cube on the GPU and like manipulate it in 3D space, it would be nice if you could upload the vertices of the GPU one time, right? So you can say like, well, this like back left corner is -1, -1, and this is -1, +1, and this is +1, +1, and this is +1, -1, whatever. I don't remember what I said. But these all have like different coordinates. But if you really want to slide that thing around the world, well, then you need to like manipulate those in some way. And so like typically your OpenGL application is going to create a vertex shader, i.e. program that runs on each individual corner of your thing that you're rendering. And you can do things in this like apply perspective and move it around the world, scale things up and down, basically like any operation that you could do, that you want, you can do that. Then this runs into this thing called like a fragment shader. It takes the output of each of these corners and it like runs. We're going to gloss over to some details here, but essentially like if you were to take one of these triangles for the cube and you were to then try to put it on the screen, you kind of have to like walk over every single pixel that shows up in that triangle. And so the fragment shader's job is to essentially say, for each pixel, how do I want to determine what color that pixel is, right? So you can do things like, say, sample from an image, right? You can like make a picture and put it on the triangle. Hand wavy, right? So this is kind of how like there's other stuff, but this is essentially like how a OpenGL program expects to work. Is you have programs that are user defined that define these things. And so in our little sample application for our simple case of drawing a triangle, we have the world's simplest vertex shader who says like take in a vertex and please output it as the position. And we have the world's simplest fragment shader that just says like make it white, essentially 1 1 1 1 1. You could make it green. You could even like this like Kurotian is saying in chat. You could even do some shading, perhaps. Yeah, you could do all sorts of stuff. So in order for us to be able to display anything on the screen that's like any shape, we basically have to implement this flow. So that's the goal for today, is to try to figure out how that works. We have implemented our OpenGL stuff by using this library Mesa. Mesa is like an open source OpenGL Vulkan implementation. The user space side of these implementations, I guess, that's like pretty common to use in Linux. And in our last, or like in a previous happy hour stream, we managed to get to the point where this doesn't crash us anymore. So what we've been doing is we've essentially been like slowly implementing functions that the Mesa like system expects us to implement, right? And basically anything that we haven't implemented is 0, is a function pointer to a null pointer, which means that anytime Mesa tries to use it, we just crash our program. So every time we add a new function call to our test application, we just start segfaulting, we look at where the segfaults are in GDB, and we add a function to like not crash there. So these are the functions that we had to add in order to not crash this triangle drawing application sample, right? And we start to see some like interesting names in here. We see create VS state, create FS state, which we can probably assume is a vertex shader and fragment shader. We see something about like buffer subdata, and if you've worked with the OpenGL API, it's like, oh, that sounds a lot like setting the data that lives, like setting the vertex positions, right? You have a bunch of inputs to your shader program, which are all of the points in the world, right? This is like kind of like uploading those, probably. That's my guess from the name. Something about like depth, which we probably don't care about right now because we're kind of trying to render a 2D triangle, so we can probably skip these. Binding of fragment shader and vertex shader state, so you can probably assume again that like the OpenGL world, you compile your shaders into like some sort of like representation, and then later you say, okay, I want to like use these now, so we can probably assume that this is that. And then there's some stuff in here that I think blending, I was looking at blending like this morning, and it looks like blending is related to like transparency, like if you wanted to like do like a tinted window or something. I think that's what this is for. Rasterizer state, I'm not sure. I think that this is like probably trying to like, if your GPU, well, we can look at the parameters here. I think that this is just basically saying like set up triangle rendering in this way, and I think that it has like parameters for that. Viewport, I think this probably corresponds with the call to GL viewport, which basically says like how big is my window. When you're doing conversion from like normalized coordinates to like pixel coordinates, you need to know where the pixels are, like how many pixels your monitor has. And then I don't know what this stuff is. Maybe we need it, maybe we don't. Vertex element state does not sound familiar. Set vertex buffers sounds a lot like binding vertex buffers, right? So saying like, okay, we've uploaded like 4 models. Which model are we rendering? That's probably what this is. And then draw VBO, I would guess, is like actual do the work. Now, this is all like really educated guesses. I'm not really sure what's going on here. I'm just like reading the names and guessing what has to happen. But it sounds kind of right to me. So if we like go into this code and we kind of look at like the parameters that they're passing to us, we can look at something like create VS state, and we can like look at the input parameter here. And this looks a lot like shader representation, right? So I think what happens is probably like when I write a shader, when I looked at that like, what is it, source, test app, vertex, source maybe, vertex GLSL. When we look at this, right, this is what we give to OpenGL. Well, this surely isn't what like the GPU executes, right? So my understanding here is that we write like this language called GLSL. My understanding is this goes into like Mesa, kind of hand wavy, Mesa, right? And Mesa, before we have like an implementation in here. So Mesa is going to give us some sort of like intermediate representation of the shader, and that goes to like us, where us is like the driver writer, right? So today's goal is to try to figure out how to get this into something that's like on the GPU, right? So we're gonna have to go through like kernel space. We're gonna have to talk to our driver, right? We're gonna have to talk to our driver. We're gonna have to like convert this thing into something, give it to our driver, and then the driver is gonna have to like upload that to the GPU, right? So this is gonna go to like GPU, and this is gonna like upload stuff over here. We're gonna figure out what that means. But yeah, we'll see. I don't really know yet. The last piece that people who have been following along might be missing is that we have in Happy Hour also kind of prepared for this a little bit by adding this like libgpu library. So the idea here is that in our virtual GPU is implemented in QEMU, and before we were kind of just doing like whatever in the QEMU source code, it would be nice if we're creating a shader interpreter which uses our own custom commands. I would love for that like language to live in one spot. So we split out this Zig library, one, because it would be nice to have a library, two, because it would be nice to write some Zig instead of C. And we have linked this library into both QEMU and our Mesa implementation. So we should be able to go into this library and just like bang out a API and like a instruction format, and figure out how to like create that instruction format and consume it at the same time, which should give us like pretty good flexibility in terms of changing the format as we go. All right, long intro, but I think that's all the context we need to give out. So let's actually write some code. So I think the first thing I want to do is like just see if we can like inspect what the the intermediate representation looks like at all. And I was doing some Googling, DuckDuckGoing, and in the Mesa source code, I think I found something like, I was looking at this like NIR thing, which is like new intermediate representation. I think that they have two IRs. One is like, thank God it's Friday or something. No, it's not actually what it is, but that's how it's like embedded in my brain. Mesa TG SI. Thank God Saturday it's. So this is like the old version of their like intermediate representation, and then they have a new one called like NIR. For I think the N stands for new. I'm pretty sure. So I was looking at this and I was like, okay, let's like just like look up words, right? Like we type nir.c into our thing, and we see all of a sudden like this list of like debug things, which seems pretty good. Print vertex shader seems pretty good, right? And we're like, what? Okay, so what is this? Like debug get once flags nir debug. Okay, so it's like probably an environment variable, right? Nir debug environment variables nir debug. Cool, right? So we can like just look at this and we can say, okay, what happens if we call like print vs here? What happens if we type that? So we go nir debug print vs, and we run our app, and we do see a bunch of useful information, which is pretty cool. So here we can see that they took our vertex shader and they turned it into something, right? So they say like, essentially this is probably the last piece that we get before we get into our driver, where they have like something that says, okay, we have one input, one output, some uniforms. What else is in here? Inputs red, next stage. Okay, who cares? They have some sort of like inputs to the shader is called a pause, which is what we called it in our GLSL shader. They have some output called GL position. And this is what this shader turns into. So who knows what this means? They look at like, they dereference a variable, a pause. I don't know what this 32 means. I'm not sure. Maybe this takes in the address of the parameter and stores it as a 32-bit pointer, would be my guess, right? Because here they're then dereferencing this thing into a 32 by 3. So this 32 by 3 must be like XYZ floating point value, right? If we look at like our actual shader, test app source vertex, it is like a 3, like a XYZ floating point value, essentially, right? So this 32 by 3 makes a lot of sense there. This load deref annotation, again, makes a lot of sense if this is a pointer. This sounds a lot like we are looking at the address of the thing here, loading it into whatever like %16 is. Presumably these percent numbers are like variable names or registers, probably something like that. They load a constant here, 1.0, into register 11 as a 32-bit value. And then here, I guess they take the output position and put it in 15. So then the last thing that they do is probably this actual work of saying like, take this thing and throw it over there, which means that they take the input X, Y, and Z from %16. That makes sense. And then they add the last bit from %11. Cool. And this makes up the four value output. And they store. So what is 27 here? Oh, I see. I see. So this is a new instruction here. So they took 27 is like the output value. And they're saying we are taking the address of the thing in 15 and storing 27 into that address. Okay, yeah, so that's nothing crazy. I don't know what block means, which is a little concerning, but maybe we'll figure that as we go. Can we look up like, if we go back to like mesa, I wonder if they will tell us in here. Can we like search in here for like block? No. Block. No. Block. Let's just kind of block. No. Block. No. Block. Okay. Unlucky. Unlucky. Can we look for the word block in here? Not looking good. Not looking good. TR dump state. Yeah, so like I don't really understand like what a block is. State block. Determine the layout of the working block in thread units. Okay. This is in pipe grade info. No idea what the fuck that is. Okay. Maybe we just ignore block statements for now because I don't know what they are. And the rest seemed pretty straightforward. Now, that was like a human readable representation. But who knows like how they created that? I don't. So I wonder if we can like look for like usages of this thing. And I wonder like if that will give us anything interesting. So this does like searching for usages of this macro don't seem that great. Maybe those are just basic blocks. I mean, sequence of instructions without flow control. Could be, could be. Like maybe they have like, are you saying like maybe they're like almost like labels? I guess that's possible. Okay. So this goes here, this hidden by a macro, but this gets used here. So should print ner, nice. So someone's gonna use this. So, okay, so when they do like ner passes, they say ner print shader. So let's look for that function. Ner print shader. Nope. Ner print shader. Is this like a function somewhere? All of these are usages. Are any of these not? I'm looking for like a function definition. Okay, here we go. Ner.h. So presumably in ner.c, there's print shader, right? No? Oh, here we go. Found it. We found it. We found it. It just, I don't know why jump to definition wasn't working before. Okay. So presumably they can like iterate the parameters of this in some way, right? We're just kind of like guessing. For each variable with modes, then print function. So probably this is where the actual like function block is. This was probably this part up here, decal var, right? Print var decal. We're probably gonna see decal vars in here, yeah. And then here, print function is decal function. So that's this main. Okay. So this is probably the interesting part here. Probably. Ner index blocks, print CF node. What is a CF node? What is a CF node? exec node type, block if loop function. Okay. Okay. So we're looking for this stuff, which has to be here, right? Has to be. So impl, like, what is this for each list typed? He goes like, he basically rips through exec node, sure. So that's this, which is just has next, previous, and that's it. So this node must be like, you must be able to like extract some sort of useful information from this. Oh, I see. Maybe each node, maybe when you walk this thing, you can use like container of to say that I know that this is a ner cf node. This exec node is a child of this, so you can probably cast the exec node back to a ner cf node, would be my guess. So that's probably how they're walking the list here. They're saying that the type star ner cf node is equal to exec node forward data, which does God knows what. Exec node data here. Yeah. So he's doing exec list offset, which does an offset of. Yep. Okay. Cool. So this is certainly just walking the list. Walking the list of. Hold on. Field. Okay. So this thing has node. Right. So that's what this is. The node here is pointing to this node here. Got it. Understood. So if they have a block, that's probably what we're seeing here, right? So they probably put a function name somewhere. I wonder where the name gets printed. CF node as block. Okay, so this is doing ner block. This is the interesting part. Okay, so the ner control flow nodes is what the big fox is guessing. It looks like we have, since this is a member of ner block, they're allowed to basically, if this type says block, you can basically cast this struct to this struct. It sounds like that's what they're doing, kind of. Which is what this like control flow node as block is doing, is it's casting it, and then here they print the block here. So this is this, which means that the actual interesting information is for sure in here, right? We have preds sucks. And this is not an empty block, sorry. Okay, so here's where we are. For each ner for each instruction, we found it. This is the interesting part. So we go for each instruction in the block, we can extract that information. Hell yeah. And then print instruction is looking at this. Oh, beautiful. Beautiful. Okay, so probably we can try to walk this stuff ourselves. I did do a little bit of off-screen like spelunking here, so I might be jumping ahead a little bit, but I did look a little bit at usages of create vertex shader state. So I was looking at like other implementations of this thing to kind of give myself confidence that this sure is where people do shader compilation. So we do like, if we search for like create vs state equals, and we just go into like any of these implementations, right? Like we go into like R600 create vertex shader state. What does this guy do? He does some sort of processing of the shader state, right? We can see that he's talking about thank God Saturday it's or ner. We can see that he is doing like pre-compile shader compilation, right? We can like, if we jump into here, we can see them like walking the thing, probably pipe shader create. This goes into some library that we don't have installed, whatever, or we don't have like built. But I'm pretty confident, like maybe like 75% sure that when they say create vertex shader state, this is where we're supposed to compile our shader. I'm like 75% sure. I think I also saw in here, in other implementations of this thing, that you have to copy the actual state out if you want to use it. I think I saw that in the soft pipe version, i.e. the software implementation. I think I saw in here this comment that says we need to keep a local copy of tokens. It looks like also people have the choice of if they want to use new if they want to use new IR or the old IR. And it looks like this driver basically converts to TGSI if they feel like. I feel like we should use NER because it's new and cool and we're new and cool. But I'm kind of just like banking on the fact that it's not more complex, but it probably is. But we can start there and see what happens. Mesa repo also has source compiler NER readme. I swear I looked for some docs and I couldn't find them. Oh, sick. Okay, let's read this. This seems awesome. New IR or NER is an IR for Mesa intended to sit below GLSL and Mesa IR. Its design inherits from the various IRs that Mesa has used in the past, as well as direct 3D assembly, and includes a few new ideas as well. It is flat, typeless, similar to TGSI and Mesa IR. It also supports SSA. It doesn't require it. So it's got variables, sure, registers. Registers are lightweight, SSA. So every register can be loaded or stored. An SSA value can be used instead. I don't know what that means. What does SSA mean? What does that mean? Social Security. SSA GPU shaders. Let's see what that like. We'll ask the idiot. What does SSA mean in the context of Mesa shaders? Question mark. Maybe he knows. Static single assignment. That sounds likely. Yeah, assign to exactly once. Got it. So basically like constants. Functions, intrinsics. So the intrinsics are probably the at prefix things that we were seeing. Single static assignment. You've got an idiot right here. Let's go. Idiots in the chat, thank you very much. Textures and control flow. Okay. Sure. Seems reasonable. Let's see if we can figure out how to like process this thing. So taking inspiration from SoftPipe here, I think I read somewhere as well that shaders, like our implementations, need to be able to take in any type, or maybe like, I guess we can probably try doing this for now and we'll kind of see what happens. Okay, so they have like a template that they take in. Sounds like we're probably gonna do that, and we'll probably try to use it as NER. Maybe for now we'll just assert that it's NER, and then, you know, because we don't have to be a good driver. We just have to be a driver that's good enough for our one simple test case. So let's start here. Let's call this template to match what they did. And we'll just say like assert this. I think this is not valid, but it's good enough for now. SSA is when you assign unique names to all intermediate results. So they don't have to be constants. But doesn't that mean if it's like single assignment that you can't reassignment? It's an intermediate representation property that makes certain operations transformations easier. But like, am I misunderstanding that single assignment means that you can't change it, which is effectively constant? I don't understand what the difference is. Okay, so we saw somewhere that from here we look at the NER. Okay, so this is what we should get out. And what is the type of this thing? It's void star. Now, I think we also saw that in here, they cast that thing to something, NER shader. So we should be able to struct NER shader star NER. Okay. And then this is where the interesting stuff goes. But I can't jump to reference on this, which means that it's probably some header I need. So I need source, I need ner.h probably. Yep. Okay, so we will get that in here. Slap that guy here. Jump to def. Nice. Okay, and then in that like printing stuff, whatever the fuck that was, ner.c probably? No. nerprint.c, that sounds right. In here they had like these like control flow nodes is what we were guessing they're called. How did they get these? How did they get these? Print function impl. Okay, so ner function impl, ner function. Okay, so here they went over each shader function. Shader must be the ner shader, right? Yes. Okay, okay. I think that makes sense. So let's leave this open over here for reference. And here we'll say, let's just try to ignore everything for now, and we're just gonna go over their functions. So for each list typed, ner function, func node, shader functions. Now we need the shader still. So shader here, we'll just call this shader like this, boom. And let's just try to get anything interesting out of this thing. So this is an exec list of functions, but this turns into ner functions. And I think that this is probably saying that we are looking for shader functions. We're probably looking for like ner function has a member named node. Yep, that is an exec node. And we're turning that into a variable function. I think that's probably what we're seeing, yeah. So we probably want to say like, we probably want to look at the type of function here. Not ner function, of course. So can we get like its name? Let's just print its name. So we should just say like, we have a function with name, this thing. We saw ner to TGSI. There's also TGSI to ner if that assert ever causes trouble. That makes sense. Thank you. I probably would have guessed that too, but appreciate you looking up front. Okay. Let's see what happens when we do this. So if we understand this correctly, we should see main, right? We have one function main, and we should see that printed out. So let's do build.sh, which just compiles our thing and tries. Then we should try to upload it. We turn on networking in our VM, so that when we try to upload our new compiled versions of our libraries, they show up in the right spot. And let's just see what we get. Maybe it'll segfault. That would be kind of fun. Instead we got nothing. That's quite surprising. Quite surprising. Are we using the wrong test app? No? Okay, well. Yeah, kill all test app. Seems like that's right. Seems like that right. So then why are we not seeing anything printed? Maybe we don't have any functions. Let's just say in create shader state, right? Let's start there. Let's start there. Because if we don't ever end up there, then we must not understand something. But we ended up there for sure because it crashed when we were implementing this the other day. So like surely we must get in there. But yeah, I'm just really not seeing it. Okay. So what happens if we assert false in here? If that does nothing as well, then we can be fairly confident. I'm wondering if there's like some sort of like standard out clobbering that could be going on. Okay, yeah, so we definitely get in there. So why are we not seeing this printf then? That's confusing. That's actually extremely confusing. I wonder if like standard output gets like redirected by default or something, and maybe we have to like fprintf to standard error. Maybe it's something to do with using SSH. Oops, kill all test app. Let's try. Oh yeah, okay. I don't know what the fuck is going on here where it's not getting printed, but we're definitely seeing it here. So I guess don't think about it. That's very strange. Very strange, but fine. Okay, so we do see we have a function with name main, which is pretty sick for us, which means we found something. And I guess now we have to, like, I don't know, inspect that thing? So that was in here. They did. Where was the actual. Here, for each control flow node in impl body? That's what we're looking for. So we look at, like, this. What is func impl here? Ner function impl. So this. I see. So this is like metadata, parameters, stuff like that. But the implementation is the actual interesting part. And the implementation has, who are we in implementation of? A pointer to ner function impl which runs before it, once per draw or dispatch. So we might have some preamble. Who knows what blocks are yet? I haven't really figured that out. Local variables, okay. SSA, number of basic blocks. Okay, so impl, like body here is again the interesting piece. And then this is an exec list where the type of the thing in the body is ner cf node. Okay. So we should be able to basically do this, right? Boom. For each ner cf node in impl body, which is for us func impl body, can we do anything interesting with this? We have the type. Let's start with the type. Got cf node with type. Do they have like a type string for this already? Serialize. I mean, what do they do in the print thing? Oh, they just do it. They just write block manually. Okay, sure. So let's do something like const car star. What is this thing called? CF type string takes in a whatever node type was, which is a ner CF node type. And we just go return unknown, return block, return if, and return loop. All right. Boom, 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 boom. This has an incomplete type, so where does this thing come from? This comes from ner.h. Compiler should be fine. Maybe we spelt it wrong. Ner cf node type. Oh, this is not an enum. This is just ner cf. I say it like this. They did type def struct. No. Yeah, they just do type def enums. The enum's technically unnamed, and we only have the type def to access it. Got it. Okay. So we should be able to go like this. What do we call it? We called it cf type string, which comes from node type. Okay, let's see what happens. I wonder why our printfs are going away with the SSH version. I want to try. Can we try? Oh, fuck. Kill all. Best app. Okay. Okay, so we do see got CF node of type block, which is good. Which is good. We don't know what a block is yet, but we'll figure it out. A block could be like kind of like semantically equivalent to something like this, maybe, right? Like you put your stuff in some braces or something. I don't know. I don't know. Don't ask me. Okay. So ner cf node function was the other one. And here we're gonna have to actually do something, right? So Oh my god, this fucking. Ugh. I hate it, I hate it, I hate it. Okay. I don't know what I'm supposed to do to make this not fucking happen, but it makes me want to lose my mind. Every time I'm in a switch statement here, it just does something stupid. I should look into that at some point. Oh my god. Please tell me that if I do this now, I can do like. Oh my god, dude. I'm gonna lose it. I'm gonna lose it. But it's fine. It's fine. Okay. So I guess we will only handle blocks for now. That's actually fine, because that's all I know how to do anyway. So we'll assert that node type is equal to ner cf node block, because surely we won't get far enough in this to have to execute ifs. And then you can say ner cf node as block, which returns a ner block. Bro thinks he Adele. What the fuck are you talking about? I have set local C in keys, then a bunch of crap in my vimrc. You're welcome to try it. Explaining it is left as an exercise. Dude. Look at this guy, man. Oh, I lost it. Hold on, where'd it go? Look at this guy. Yeah. I will. Now that's been on screen, so I can find it in the VOD if I decide that that's what I want to do. Thank you, thank you, thank you, thank you. Okay, so if we have a block, what do they do when they print the block? I keep fucking jumping between, I keep getting confused between Vim splits and tmux splits. It's a little annoying. Okay, so they basically, somewhere they do like actual walking of the exec list. Print instructions. Ner for each instruction block. This is probably what I want, huh? Probably. Then we can just do the same thing here. Sick. Sick. Okay. Print. Okay, what if we do like fprintf to stood error? Maybe that will work. Instruction type this. He's mad because this probably needs to be a pointer here, and then this guy's happy. Let's see what happens there if we do it this way. Oh, LO by Adele. I see, because the other guy said hello. I got it. Okay, here we go. Got instruction type 145104514. All right. 1 deref 0 1 2 3 4 intrinsic load constant intrinsic ALU. All right, yeah, that seems like maybe reasonable. Okay, so now we have to process each of these things in some way, shape, or form, I guess. I assume that like ALU instruction, I assume that, yeah, all of these things have casters to go to like the right type. So we switch on the type and we like pull the piece out. Okay. Sure. So I guess, how do we want to handle this? I guess we do have to do like switch on instruction type. Case ner ALU instruction. Is this, no, it's type ALU. Oh, ner instruction type ALU. Got it. So there's a lot of stuff in here, but probably maybe we just start with asserting on anything and then fix them one by one. I guess we know what they are. We have them all printed. So we had 1, 4, 5, and 0. So we have 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 5. This is all we have in our program so far, right? Oopsies. So we can do like case this, and oopsies, the colon goes over here. Okay. Okay. Default assert false, and how do you do this? Unhandled type or something. Yeah. Then you can get the string of the assertion. Wow, 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 wow. And then here we'll just do like LU. You know, something like this. fprintf, dref, intrinsic, load const. All right. All right, let's see what happens here. Give him a sec. Cool. Cool, cool, cool. No crashy crashy. No crashy crashy. And we have the stuff. So now we can go like whatever those casting types were. So this is like ner ALU instruction is equal to ner instruction as ALU. Yup. Inster like this. And this probably has to be a pointer. Nice. And like, what is this thing? So there, I think we saw those words here. Ner ALU instructions. ALU instructions represent simple operations such as addition, multiplication, comparison, etc. that take a certain number of arguments and return a result that only depends on the arguments. ALU instructions in ner must be pure in the sense that they have no side effects and identical inputs yield identical outputs. A good rule of thumb is that only things which can be constant folded should be ALU operations. It can't be constant folded, then it should probably be an intrinsic instead. Each ALU instruction has an opcode, which is a member of ner op enum. Okay, so in here, we have op. Cool. Associated with each opcode is a metadata structure, ner op info. Where? Associated with each opcode is name. Oh, this is like a global thing. This isn't like, so I see. So somewhere here, aha. So ner op infos is like a global constant with all these things. Got it. Okay. Which shows how many arguments the opcode takes, information about the data types, and the algebraic properties such as associativity and communicativity. Commutativity. Sure, I don't know what that means, but we'll figure it. We will ignore it. Is the more likely answer. Info structure for each opcode may be accessed through a global this. Oh, we could have kept reading. LU operations are typeless, meaning that they are only defined to convert a certain bit pattern input to another bit pattern output. Right, so that's why we saw 32. We saw those like 32-bit values in the shader dump, but they didn't say that they were floats or ints. They just said they were 32 bits. The only concrete notion for types for a ner SSA value or register the only concrete notion of types for a ner SSA value or register is that each value has a number of vector components and a bit size. Yeah, okay. Ner doesn't have opcodes for int bits to float and friends because they are implicit. Okay, even though ALU operations are typeless, each opcode has an ALU type metadata for each of the sources and destination, which can be floating point, boolean, integer, or unsigned integer. The ALU type mainly helps backends which want to handle all conversion instructions, for instance, in a single switch case. They also implement when a backend requests the absolute value, negative blah, 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 blah. Okay. So, presumably, there is like a defined number of ALU operations, right? So, like, what are we looking at here? Move. Which doesn't really tell us what it does, huh? I sign. Oh, yeah, how am I like, I mean, we could guess, right? But do they have like a real definition of this thing? Like, scrolling. Like, how am I supposed to know what this thing actually does? Because I feel like when I was looking at the TGSI docs, which I think were in Gallium TGSI, these told me like exactly what they do, right? This said move, takes the source and sticks in the destination. That seems like something I can understand. This feels a lot more unclear to me. Maybe this is what they're talking. Maybe it just goes in here. So, right. So move. No, I don't see it. I mean, but like I not here is telling me that this is like negative description. Invert every bit of the integer. So I guess they're just kind of saying that move is so obvious that they don't have to explain it. Not sure. Not sure. How do I know? So like ner ALU. Well, I think there was other. Okay, so there's opcode reference here. Oh, this is where we were. Ner opcode reference definition of behavior. Is that like something that exists? Mesa. Fuck, this is a little annoying. A little annoying, but maybe we just have to like use our brains a little bit. Okay. Let's I guess just start by trying to like extract the operation. So if we have an operation of something, where are like the parameters? Right? That doesn't seem clear to me at all. So what are they doing here when they print it? For each of the number of inputs, they print the source of that thing. Okay, so then they get I gets passed in as source here, which is instruction source. Okay, so I would imagine that we don't have to actually iterate that like ner instruction info thing, because like presumably the instructions should be defined, right? This is kind of like generic printing, but we don't really need to do that, right? So we should be able to go like switch ALU op case, and then we can like handle whatever cases come up, right? So I don't know. For now, let's just do something that's like, is there like an op to string? Ner op string car const ner op. Nope. Car ner op. Yeah, okay, we can just do it ourselves, fine. This is a very Vim macroable thing. But I just want to like start printing out what we need to implement. Was there a ner op info name? That's actually very possible, huh? If there is, we should use that. That just makes a lot of sense. And there is. Yeah, okay, let's do that. Thank you. Thank you. Okay, so we should be able to go into here and say, basically we'll just say default here is assert false and fprintf stir unhandled ALU operation. This. Maybe we won't even assert. Maybe we'll just log it. And so we go ner op info ALU op name. Yeah, maybe. Ner op infos. It's plural. And then we break. Is he gonna get mad at me for like having a useless switch there? Maybe, but maybe not. It'd be cool if he didn't. It would be cool if he didn't. Unhandled ALU op vec 4. Oh, and this is the only type, the only time. Okay. All right. Cool. So there's only one ALU operation to implement, and it's vec 4. So let's look at that. So vec 4. Okay, so presumably we have to do something here. I don't know what yet, but you know, we'll get there. Vec 4. Nice. So this just does a copy. Cool, yeah. So what are our inputs? We have source 0, source 1, source 2, source 3. This outputs thing. Okay, so can we look at those things? Can we do like for... So these aren't going to be like numbers we can look at. These are going to be like references to a thing, right? Presumably, right? Because this is like, for each vertex, we're going to be doing this thing. This is going to be pointing to some other... It's got to be like a pointer, right? So can we look at what they do? They iterate over... So for each source, they print the source. So we should, as far as this goes, it seems like we should have 4 sources. So can we look at like ner op infos, ALU op num inputs? This should equal 4. Num inputs to vec 4 is this, right? Let's kind of start there. Let's start there. Let's just start small. He's thinking. Yeah, so he has 4 inputs, so that makes sense. And can we like look at these things? So we look at like ALU source 0. Like what is this? Base source, ner source. Okay, so how do they use this when they print? They probably like extract the name somehow. Swizzle I. Printf. So they have ner source num components, which they extract from the SSA here. And then do they get the index? Is the index how they print the number out? When we called this before with like, what was it? It was ner debug equals vs. It was in ner.c. It was print vs. Okay. This should tell us. Fuck. Are we already running this thing? Kill all. Yeah. Okay. So we are looking at this, and they have the register dot the name, hand wavy, right? So in their print, this must be fprintf fp the dot here. which means that they must have printed something before that, right? They must have. Live channels, use channels. Ah, okay, hold on. So they go over the vector components. And if the swizzle equals I, print swizzle is true. If print swizzle other and this, if print swizzle or this, then we do stuff. But where's like the, oh, here, this is the actual interesting part. Oops. Print SSA. So this is what we're looking for. So how are they getting like the name out of this thing? I'm mostly interested in like how we're supposed to tie this back to anything. Generic definition index seems kind of likely here. Maybe we print out an index and num components here and see if that helps us. Oh yeah, here they have index. Where's their like actually print? Print const from load. Yeah, here we go. Maybe. Eh. Define print values. Jesus Christ, dude. Okay. I'm like putting a bet on index here. Bit size of each channel. What are channels here? I'm not really sure what channels are. Oh, num components. Probably num components tells us is going to say 4. No, because this is four independent inputs here. Def index on 392. Ah. Yeah, that seems kind of likely, huh? That does seem kind of likely. So the guess was kind of right. What's num components here? I guess our num components will probably be 1. We're probably going to see one component because we've split up our vec4 into 4 individual things. So I bet we're going to see like this. No, num components. We'll say like we got like a vec4. ALU op vec4. We're going to say the num components is this. Index is this. Okay, that seems reasonable to me. Somewhat. PCI channel? Probably not. I really doubt that. I would guess that channel is going to be like the subcomponent of the type. Num components 3. Oh! Hold on. That makes sense. We're combining a vec3 and a single integer. So we have to like decompose that vec3. It seems like. Okay, yeah. So can we look at like the sources here? Do we have like a number of sources here? Number of inputs. So we know that this is supposed to be 4, right? So for int I equals 0. Wait, no. It should. We saw 4. So num components is 3. Do we have SSA, num components? Okay, this was index 16, so that at least lines up. That lines up with what we saw printed here. 16 here, and the vec4 is 16xyz. Okay. So I'm missing the piece here of within I would think that there should be 4 sources, right? That's what I would think. So can we go for int I equals 0, I is less than 4, plus I, do this. And then I expect to see like the number 16 3 times here, once for each of the x, y, z component of that vector, plus one index of the other version, or the other variable, I guess, the like constant 1.0. Yes, okay, so we see 16, 16, 16, 11. And so now the question is how do we pull out each of the individual values? Right? Which means that we're missing a piece here where the source must tell us that somewhere. Swizzle source. It has to be in here, right? It has to be divergent bit size index uses. Oh, it really doesn't feel that way. Really doesn't feel that way. So how are they getting it in the printing stuff? It must be in used channels. Okay. So we look at the, or it could be the swizzle. So if we have print swizzle, then we iterate over which channel is used. So channel is here. Swizzle here. So for each input argument, it says which component of register it is chosen from. Note that which elements of the swizzle are used and which are ignored are based on the right mask for each opcodes. For example, a statement like foo.xzw or var zyx would have a right mask of 1101 and a swizzle of 21xo. Aha! I see. So in here, how do we know? So here we ask, is the channel used? By looking at input sizes. Did we have that somewhere? No, that's in an op infos. So input sizes tells the number of components in each input. Okay. Can we just look at the swizzle value? I'm missing a little bit about like swizzle I. It's not equal to I. Print swizzle is true. Because I imagine that the swizzle is going to have like just 0 and then 1 and then 2. That's kind of what I imagine. So let's just start there and see if that makes sense. Is it here? Where is the swizzle? Here. Okay, let's start there. I guess the swizzle wouldn't make sense for the constant input. Only for the vec3. Only for the vec3. Okay, no, this seems like somewhat reasonable, right? So we see 16, 0, 16, 1, 16, 2, and 11, 0. Okay. However, I'm a little hesitant to say that the swizzle makes sense on the other value. What do they do here? They just write 11, which means that print swizzle is untrue here. Okay, so they say here, as we, I think I understand. So this NIR ALU instruction channel used is tells us how many of the swizzle things there are, right? So this uses this should tell us 3, right? We look at op infos for our operation, input sizes of this source. So where does this come from? ALU. So this, we already looked at this though. This is 333, right? Number of components. I think we saw, or input sizes. Input size. So this comes from this. So this comes from our ALU op. ALU op and the input sizes of I. Okay. Let's see if we can understand. Let's see if we can understand. Give it a sec, give it a sec. Okay, yeah, so we have input size 1, 1, 1, 1. Got it. And so what happens there is they have here that the channel is not equal to I here, right? So we're going to have like one channel, right? So we're going to have like, this is going to be indexed with 0 every time. But the swizzle value at that thing is going to be different than the index. So then they're going to print this thing as a swizzled thing. I think that makes sense. Okay, I understand. Otherwise, they just look at the register value directly. Or the SSA value, whatever we want to call it. Okay, okay, I think that makes sense. Now, how would we implement this thing? I think that before we implement the vec4, we need to implement the load, right? The load is the first thing. Just get some values tagged in memory somehow, right? So let's start there. Let's start there. Let's implement any instruction. I think we have kind of poked around the NUR enough to the point where I feel like I understand what it's trying to do. And let's just try to figure out how to fucking get this thing working. So, let's start with the deref, since that's the first thing, right? We have deref and load deref. Do we see that in our output? Deref, intrinsic, load const, deref, ALU. So ALU is this part here, the like actual math. So this corresponds with deref. Intrinsic is the load deref. The at sign is the intrinsic here. So load deref is an intrinsic. Load const deref thing. Okay. So we should be able to implement this. This seems like very possible. Let's start with deref. So what does deref even mean, really, right? NUR. I don't want like NUR. We're only seeing like texture instructions and ALU instructions. It's neither of these, right? Yeah, there's like texture deref. Is there like kind of like documentation of what these are supposed to mean? I mean, we can take like a pretty good guess, but it'd be nice to have like real documentation. NUR inster type deref. Like, what does this mean, you know? NUR deref, see? Okay, let's look at this. Not sure. Not sure. Can we just go back to our thing and try to handle the deref reasonably? So what do you want to do here? I guess we want to look at like NUR printf.c again. So if they print deref, they look up the var name from the state. So it's just instruction var, or inster is a NUR deref instruction, right? So we probably do like the same like conversion here, where we say NUR deref instruction. He's mad here probably because NUR deref instruction probably needs like NUR deref to be in here or something. Just kind of hand wavy. No. Ner type def. Ner deref inster. This is in ner.h. Okay, seems fine. Am I fucking mental? Okay, this exists. I feel like I'm losing my mind. Yeah, that compiles fine. So the fucking indexer is just confused and broken. Okay. Can we just restart? Dude, come on, man. That's so annoying. Ner dref inster. All right, whatever. It's fine. So the type could be any of these. Okay. Modes, bitmask of what the underlying modes might be. Type. Can we just look at like, I see. So if it's a parent deref, we have some behavior. So I guess we just start with looking at the ner deref type. Okay. Seems reasonable. So deref type. And printf ner deref type is this. I don't know what the fuck is wrong with playing D. That's really annoying. But, you know, we will live. We will survive, however annoying it may be. All right, so we get hello? Why am I not seeing a deref type? Maybe it's not compiling. Is it confused? Shouldn't be. Oh. I forgot, in SSH, for some reason we lose the, we lose our standard output. I'm not going to think about it. It's not important right now. All right, there we go. So ner deref type 0. So we're only seeing deref types of 0, which is the only thing we need to handle then. So, boom. Assert deref type is equal to this, right? That means that we can just kind of move on with our lives and look at the variable. So the variable is going to be like, what the fuck is a ner variable? And also, like, doesn't this need to like output to something? How do we determine like our output variable? Definition to store the resulting pointer. Nice. Okay. Okay, so we're gonna be like storing. We're gonna be like, we're gonna have some sort of like compilation object, right? And here we're gonna like push an instruction to it. And it's gonna be like looking at deref var, right, to get us this thing. And he's gonna push that as the output index. Right? So this is gonna be like push. We're gonna like push our shader output, compiled shader, lib GPU shader append, maybe that seems right. Shader append, but this is gonna be like this specific instruction. So append deref. Okay, and that's gonna be like, I'm gonna take this input variable and assign it to this thing somehow. Holy shit, there's a lot of stuff on here, huh? But presumably, like, this apause is going to have some form of like index as well. Hand wavy. Yeah, that seems reasonable to me in some way, shape, or form. So maybe let's start thinking about how we are going to represent this in our libGPU thing. So maybe we go like this. And I don't know, we'll kind of like just start typing and we'll see where the wind takes us. So let's do something like, can we make source like shader zig? And our lib will like import that thing somehow. I don't know. Do like const shaders, you import shader zig. And in here, we're gonna have like some sort of shader, right? And he's gonna have inputs. Which, I don't know. These are like some sort of like input, right? Something like this. We're probably gonna have like an input that could be like, you know, many types of things, right? But we'll start right now as like you have a vec3, which is going to be a vec3, right? I don't know. Right? This is going to have many inputs. So this is going to be kind of like a slice, right? And we're going to have like outputs as well. So maybe this input and output is going to be like a variable, right? Okay. And then we're going to have like SSAs, right? Which are just going to be, I guess we kind of have holes in this SSA list. So we're going to do this as like a hash map, probably. Right? When we look at this, we're seeing like 12, 16, 11, 15, 27, right? So for now, instead of thinking and doing something intelligent, we're just going to be like std auto hash map from an index to what, a variable, I guess, right? So we need like vec3s float. Are we allowed to do this? Is that legal? I hope so. And vec4, right? These are like the types that exist. You know, it's just like the types we're seeing here. Okay. So now the shader is going to have some sort of like list of commands, right? Which probably end up as like command, right? So here we're going to be like command is something, right? And we are going to implement like, so I think deref var, it looks like is like telling us that this thing is a reference to another thing. This is like pointer assignment almost, right? So our command is going to be like, gonna do something that takes a value from one thing and gives it as a pointer to another thing. Okay. I guess we'll kind of have like unassigned as well as here. Unassigned. That's kind of how it looks like we're going to start. So maybe we kind of what? As we like push this thing, we're going to have like push command. I don't know. Right? I guess for now, we will kind of make this a stood array list. Like this, probably. And then we have like our allocator here. In an ideal world, I think I usually make these like builders. But for now, we will just kind of say, once this thing is constructed, you know, don't fucking touch it, but don't modify the list, but, you know, whatever. That's a job for later. Okay, so here we go. Fix me, add a builder. Okay. And so if we push a command to our shader, fix me, I guess this is like, this is more like shader builder. Okay. So we like push to this thing. We push a command. Simple, right? And so the first command that we see is going to be make pointer. So making a pointer doesn't actually have to be a command. We've kind of just defined, this is like defined off rip, right? So we're going to have a variable that is a reference to a something. I guess the reference is just U32. However, our like inputs here are not like, don't have like indexes like this. So our reference has to be like a reference value here, I guess. Right? And our reference could be to any of input. I guess it's going to be a struct. So it's going to be where like source, which is going to be a reference type. Yep. So we have like an enum that says like input, output, or SSA, right? So then this thing can point to one of those things. I guess even SSA isn't one of the options here. We can only be a point. We only have deref vars for position, so we're gonna only have maybe SSA is an option. Maybe we can make a pointer to one of these values, but it looks to me like the reference here is just like to whatever. So kind of up front, we're gonna be like make references. Or maybe just like push var, and this will be push command. Okay. Yup. And so here we're gonna be like, so I'm thinking we'll pre-jack it with the numbers, I guess. We'll have like, we also need like an index here, right? Or ID, we'll call it. So here we go, like self SSAs, put ID variable. Nice. Yeah. Okay. So then we can kind of just put all of these up front, and the variable, I guess, we're actually gonna like make var here, and we're actually gonna just kind of initialize them as unassigned, right? I think that makes sense. Because until a command is run that actually puts the data in this thing, we don't need to set the type. Now we're going to have a command that's like load reference. Okay, and this is going to have the reference. And the index, or ID. Yeah. So this is just commands dot put append. Okay, wait, this is starting to make sense to me. It's starting to feel like it makes some sense. So now what we have to do is, like, if we're going to execute this thing, we're going to go for self essays, because this is the only thing that can, like, change over time. We're going to, like, set that thing to unassigned. Yeah, that's making sense. And then we can just run the fucking shader. So for self commands, we switch on the command for sure, right? And if the command is load reference, we can say that self SSAs at LID, I guess it's like put, is going to be a reference from that thing. And I guess we probably don't even need to pre-jack them, actually. Right? We don't have to do this make var thing if we can just put the thing in here at this point. Okay, so then we're going to have something that's like, we're going to dereference a thing as a type, right? That's kind of going to be the next thing. It's going to be like deref. And this is just going to be like which we're going to have like the ID. So the deref goes to an output. It goes to an output, right? We have like the deref of 12 goes into 16. And we're going to have to say like, what is the expected type? Which makes me think that we actually kind of want like variable type here is an enum that's like this. And then can I say, is this like legal for in this language for me to be like union based off variable type? Is this allowed? I think it is, right? If I don't do this, does it get mad? I'm not 100% on this. Maybe we should just zig build just to see what fucking happens. I guess all of this stuff gets compiled out though, which is going to be a pain. Can we do like a pub export function something void? And can I do like shader execute or something? I just want to like see something complaining. Yeah, this is like isn't doing anything. How do I like, is it like ref all decals or something? How do I like force this to get used? Can I, how do I make it work? Zig, force function to be exported. Like, can you explain how your virtual GPU works? Never heard of it. Yeah, so we're just trying to understand a little bit how a real GPU would work. So we are basically trying to implement the graphics stack for a virtualized PCI card with like an OpenGL implementation to force ourselves to understand exactly what a GPU would have to do, even if it does it in a stupid way only in software, right? So in the same way that your virtual machine pretends to be a computer, we're making a virtual GPU to pretend to be a GPU. So these guys have like an example here. Is there like a way around this right now? Mm. God, I know it's possible. I just don't remember how to do it. Not sure. I know it's possible, but I guess for now, like instead, there's like ref. Oh, here they do this. Nice. That's what I'm looking for. That's what I'm looking for. So in lib.zig, they do a little force shader module to be evaluated. Nice. Okay, there we go. There we go. We're getting compiler errors now, which is huge for us. So now we can like export our like shader API through this module, which is works for me. Works for me. Okay. So what was I unsure about? I wasn't sure if like the variable stuff works. So if we just do like shader init here equals how do I do this? We'll be like we have an allocator. Which I guess we want to share with the main library here. We have like global GPA. I guess can we do like source globals? Global zig, stick the GPA in there. This feels like that works to me. Const globals equal to global zig. Then in our shader, we can import that same thing. Okay, and then down here we can say const alloc is global GPA allocator. Then we can create a shader here. So we go, all of this stuff gets default initialized. Like this. Okay. Right, then we can just create this with shader alloc is equal to alloc. And then we can try like testing something here, right? So we can be like shader push command. Yup. And we can push a command that's like load a reference, right? With ID equals like 0 and reference is something. Input equals like 0 and source is equal to input. There we go. Yeah, so we're going to say, hey, we get ID 0 from input 0 is what this is saying. Right? Then we probably want to set the inputs and outputs. So input is a variable. Okay. Okay. And we probably want an output as well. It's all coming together, I think. I don't fucking know, man. Let's think. Are you making a static lib? Not sure if exports get evaluated or not. I am making a static library, yeah. I am. I think that this is getting evaluated because we were seeing compiler errors here when we tested with something. When we put the comp time in shader, or sorry, in mains libzeg, we put a comp time like this, and that forced it to get evaluated. At the very least, it's like we saw compiler error in here. We'll see if we have more issues later on, but it seems okay for now. Okay. So then we have like a deref of that thing. So let's try implementing that. So we'll say, yo, I want to deref this reference into output. Okay. So we have the input to output. Yeah. So we're dereferencing input 0 to output 1. Okay. And so what that's going to look like is we're going to, I guess, we're going to put the something in here. So we're going to be like d output is going to be some variable that we make. But we have to get the thing to put in there somehow. So the thing that we're going to put in our SSA is a variable. Oh, so we just copy the variable from inputs. Yeah, so we say input val is equal to, we look at the SSA. Okay, so you say self SSA is get at ID at the input, right? I think this is or else return error invalid reference. Okay, so this gets us a variable. So if input is not equal to reference, we have like a fucking major problem. So return error reference not derefable. Reference not reference. That seems reasonable. And so then we know it's a reference. And the reference is source reference type input output. Okay, so we just switch on the thing. Input reference source. If it's an input, we look at the input array. So here we just look at the this must come from like the reference type. It must have like reference index. We must have had that somewhere. Reference index, I guess we'll call it. Okay. And on output, we look at output. That's simple. Yeah, and then this is going to be the reference val. That seems right to me. That seems right. So we at some point we add an input. We say let's do that. We say shader push input, right? We're gonna say that the input is a vec3 of x equals 1, y is 2, z is 3, right? Okay. Are we really parsing shaders? Yeah, we're going for it, dude. We're going for it. So if we then push a command here that says, I want the first thing to be set the value at 0 to be a reference to input 0, then we dereference the thing at input 0 to output 1, then we should be able to like look at the value of shader SSAs at 1. Can we turn this into a test? That kind of feels like what this is turning into, right? Test. I don't know. Shader basic execution. So now our allocator should be like stood testing allocator. Instance, I think. Allocator. And at the end of this, we just want to be like expect equal. This should be vec3 1 2 3. So it should be something like x equals 1, y is 2, z is 3. And this is supposed to be tried. And then we need to add testing to our builds. So I think we do like, how do we do this? Zig build system. I don't remember how testing works. Testing. Test targets, build, B, add test with root subs. Okay, sure. Root source file is equal to B path source libzig. And do I need to do anything else? Target is equal to target. Let's see what happens. Add test, step compile is ignored. So then we have to like add a run unit test thing. Yeah, here we go. Okay. Boom, boom. Tests. And then we need a test step. So they probably, we make one with like const test step is equal to B add step, add step test. Run tests. Like this. Okay. Let's see if that does what I think it's going to do. Yeah, you're saying that my testing was fucking wrong with my like expected and unexpected. Yeah, I think that's likely. Shader zig 124. So he's like input does not have a thing. What does it have? Index. Okay, sure. Is expect equal is mad, sure. So this is supposed to be expected. So this is a variable vec3, and we're trying to get this from like whatever the fuck we had there before. Like this thing. So this should be a variable here. And then what's he mad about? This goes like this. This goes like this. This goes like this or something. I don't know. Self inputs append is mad at 69 because we need self alloc here on all usages of our unmanaged arrays. That is true. Then we need to put exclamation points on these because they can fail, which means that push input is going to be mad because I didn't write try here. Presumably push command is going to have the same fucking problem. Okay. So now he's just pissed off because it didn't work. Okay. So let's maybe try to understand why. So this SSA is get at 1. Oh, because we didn't run the thing. We do need to run the shader to run the shader. Okay, so he's mad at items in a hash map. That's a really good point. So we need like a var like SSA iterator is going to be self SSA's iterator. We go while SSA IT next. It shouldn't need the variable thing. I thought that it was going to struggle with the resolution of the optional, but maybe I am wrong. Maybe. So this gives me an entry. And we're going to say item dot value pointer is equal to unassigned. We can try removing that variable thing and putting a dot. I thought that it was going to struggle, but maybe not. 86 self commands items here. All right, what's in that now? SSA's put. This should be, we need an allocator when we put stuff into our thing. That's fair. And expected variable found reference. I see. So we have to kind of do the same thing here, that when we... This needs to be a variable here of type reference. There we go. Okay, we're getting better. We're getting better. So now he's mad at incompatible types. Yeah, so I think here we do have to write variable. Yeah, he seems much happier there. Okay, now he's just mad at leakies, which is fine. So we should just defer shader deinit here, and we will kind of clean up our mess. Okay, so this should be like self inputs deinit with alloc, and we do this with like outputs, SSAs, and commands. All right, that's a really good sign. So we have now implemented our first two commands, load reference and deref. And now we need to implement whatever else is left here. So load constant is the next one. So I guess this is going to be like id32 and val is a variable. I guess. I'm not sure how happy I am with the name variable. I think value probably makes more sense, but you know, whatever. Okay, so load constant is going to be, you know, something that's like it's basically going to look like the load reference, except we have a variable straight up, not a reference anymore. So we can just kind of like copy this and delete this stuff and say we're going to look at l.val. Boom. Simple. So we should be able to add like another input now. We don't have another input. Okay, so we should be able to push a constant here. Okay, so load constant. And what does our load constant look like again? It's ID and variable. So we should have like the ID here is going to be 0, 1, 2, okay, or a new variable. And the value is going to be a floating point value of 1.0, right? Simple. That's what we have here, a constant of 1.0. Our test should still pass. That shouldn't change jack shit, but it should still compile, which is pretty big for us. And then they want to load a reference to the output, right? So next up, we have ID is 3 to output index 0, which means that we probably need an output in here at all, right? So we'll say push output. And I don't know if this like output needs to be typed. Not really sure. We can like kind of shove a vec4 in here for now. Okay, so we put an output of 0, 0, 0, 0. And then now we have to implement the move, right? So we're going to have a command of move, I don't know, move 4. So we're going to have like our output index, right? And we're going to have our inputs. We're going to have like our x, y, z, w. Except this isn't how this works. These need to be references, right? These are saying I'm going to be coming from not an input or an output, but a variable. Okay? That seems reasonable to me. Now, there might be a sub-index, which they call channel in the Mesa side, right? So here we're expecting to like index into our vector, which kind of makes me think that these should be implemented as like this, just to make our lives a little easier. You know? That just kind of feels like it's going to be simpler. Which means that here, anywhere we hit X, Y, Z, we have to go like this. Does that compile? Reference is missing channel IDX 150. Okay, so reference here. I guess we might have. Well, for now, we can kind of say that. I think we need a new type, actually. Can we call this like a sub reference? Channel reference feels nice to me. We're probably gonna have to do something more intelligent if we start having to do like swizzling. Like if they have like a four-dimensional vector, and we're trying to extract two components of it, we might have to start getting clever there. But maybe we can get a little bit. Maybe that we can say that like we don't support swizzling, and we'll have to handle that on the Mesa side. That seems very possible. Okay, let's do this. So now these are going to be channel references. And maybe we'll do this like for channel reference. Boom. Okay. Cool. Cool. Does that build? We're close. We just have to implement this thing. Okay, so now if we have like a move 4, what are we going to do? We're going to be like, we are trying to make an output is a vec4, right? And I guess these are actually going to come from like X, Y, Z, W, right? Hand wavy, which means that we have to make that thing. And we're going to like take that stuff and we're going to put it in our output. Hold on. Yeah, so that's fine. So this goes into like M output. And we're just going to be like const x equal to M input 0. And I guess we're going to want to like resolve channel reference. Kind of feels like what we want, like resolve channel ref. You know? This just kind of hand wavy feels like the right thing to do. We're gonna have like ref dot in source. We're gonna switch ref source. And we'll say const source slice is equal to this. And we go like input is equal to self inputs items. Right, and output, we have self outputs items. Easy. And then we just return self source. I guess we have like const var is source const val source slice at ref sub index. Okay, that makes sense. And then we have to switch on the val. And if it's a vec3 or vec4, I wonder if this will work. Can we do like return v? Oh, this is index and this is sub index. So this should give us like a single parameter out of a vector. else like stood debug assert false or something for now. For now. So then we can like resolve the channel reference of m input 0. And we just do this 4 times. Right? Fuck it. Yeah. That feels like it might be right. Feels like it. So then can we execute the move? So the move should be like move 4. Input is going to be something. Output is going to be a new ID of 4, right? So it's going to be like, what is in input here? 4 channel reference. So this is the thing. We're going to have like 4 of these. So source is going to equal variable, right? Index is going to equal the variable that we loaded from the input. So this is ID 0, subindex 0. And we're going to do this 1, 2, 3 for the first 0, first, and second parameters of that variable. And then the last thing is the constant that we loaded, which is ID 2. And I guess we have to support the fact that that thing might be a float. So we're going to have like, if it's a float, we're going to just like assert that ref sub index is equal to 0, right? And then return f. There, I think that's fine. I think. Then what is our expectation here? When we finish running this thing, we've run our move, and so we're expecting that the value at 4 is going to be a vec4 of 1, 2, 3, 1. That's what I'm expecting to see. Switch must handle all possibilities at 114. Oh, here, variable. Dun, dun, dun. For now, I'm just going to make that else stood debug assert false. And I'll just write like unsure if variables should be handled here. For now, we're in like prototype mode, right? We're just kind of like ripping shit out and we'll see what happens. I guess we need a panic. Unhandled variable reference, I guess we'll call it. There, now he's not mad. 122 is mad because we need to write self in front of all these. Sure. And then source slice at 134 is mad because right, so we actually have to handle this. So I guess this is true for the source slice index. Okay, so here we have to do like val is equal to something. We can't, we have both a slice and a map, so we can't do this way where we kind of do it all at once. We have to do like input, output is going to be ref index like this. And then on variable, we have self SSA's get ref index. There we go. Yep. Or else panic. No reference. We'll do like proper error handling later. I just don't really want to deal with it right now. Capture group with incompatible types. All right, so this doesn't work. So we have to do vec3 and vec4 independently, which is fine. It's not the end of the world. And then here we need to panic unhandled. Unhandled ref type. I don't know. Whatever. I don't care. I don't care. Okay, unhandled ref type. So he doesn't like this. He does not like that at all. Resolve channel ref. So I have variable, 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 variable. 0, 0, 0, 1, 0, 2, and index 2, 0. T2, thanks for the raid. Much appreciated. What's up, you guys? What's up, you guys? For those of you who are just popping in, we are working on adding shaders to a virtual GPU we're working on. So the idea is we want to someday make a graphics card on an FPGA or something, but we have no idea what sane design for that looks like. So we're implementing the entire software stack on Linux in order to understand what it would have to do. So we're kind of like in QEMU, making like the world's worst GPU, trying to basically implement whatever commands on that thing that we have to, so that when Mesa asks the kernel to do something, the kernel passes over to our PCI device, bing, bang, boom, it does what we got to do. So we have like a GPU driver, a Mesa implementation, and a QEMU thing. Right now, all we can do is clear the screen, right? Nothing of importance. But we are getting to the point where we want to draw a triangle on the screen, and to draw a triangle on the screen, you have to execute a GPU shader. And so we are slowly stubbing out like a GPU shader executor. So we have today just added the, like, this is all new to us today. We've added these 4 commands to map to the 4 commands that like Mesa is giving us, right? They're saying like we want to load a variable. Yeah, load reference, load constant, do a move. Our GPU shader basically does nothing but just like copy inputs to outputs. And then we just have to store that thing in some output somewhere. So I guess we have to do that. So I guess that's kind of the opposite of deref. So we're gonna have some sort of like store function. Well, first, did we? Are we? I got lost. Unhandled reference type. Right. That's what we were looking at just before the raid. So here, when they are trying to move a 4-dimensional vector, well, they as being us, our test, he's mad because we're trying to resolve some reference that does not have a type that we understand, which means that index 2, 0, 2 or 0 must have the wrong type. Is that what I'm looking at? Index 2 or 0. Right, so index, like, maybe we should print what the type is? Can we do that? Is this allowed? Can we say like type name of type of val? Is that allowed? Or maybe we want like type info? That feels, I kind of want to know like which one it is. I guess we just print like any here with val. That makes more sense. Expected 1 argument found 2. So I guess we can't panic like that? How do we fucking like crash with a message? I thought we could do that. Tag name maybe? Yeah, that sounds right. But then I guess we are still kind of in the state where we have to figure out how to panic with a value. I guess we just do this. Unhandled ref type any. Let's just do this. Good enough for me. Good enough for me. Okay, so he says that it's a variable that is a reference. Oh, right. So it's because we made it so that our move came from. Oh no, these are variables. So our load reference, load const, probably load constant is the one that's being mad. Can we look at like the index here? So can we just do like stood log error hello just to see how many times this is called? I assume that this is on the 4th input here. That's kind of my guess here. No, it's actually right off rip. So what's going on there? Oh, it's because we're supposed to look at the deref. A dumbass. This should be index 1 here. 1, 1, 1. There we go. Because we dereferenced the reference. There we go. Okay, so we got hello, hello, hello. And then something didn't work. Oh, he's just mad because there are logged errors. Sure. So our thing works. Hell yeah, dude. Hell yeah. Stood debug panic. Okay, thank you, two-step. Thank you. That's what I was looking for. So that's really good. So that means that like our whole program is almost like representable by our thing. We are just missing the final output, right? So we need to implement the store command. So we're going to take the thing that was the output of our move 4. So we are going to store this in a reference, right? So we're going to store the thing in 4 to our reference value. So which is here, 3. Okay. Yes. So we need to implement that. So we have store now, which is kind of like a deref. I guess deref should be called load. That kind of makes more sense. That's sure. And then store here will be like he's gonna look very similar to this. But let's think here. Well, I'm actually not so sure. I'm not so sure. So we have our input, which is from our variables. That seems straightforward. The output is where does like our load look like? So he takes in input here. So before their input was an SSA? Hold on, that doesn't make any fucking sense. Reference val is input reference. Oh yeah, okay, wait, that makes sense. So the input is the reference, the output was the value. For us, the input is the value, and the output is the reference. Right, okay. Okay, so we do this same thing here, but everywhere it says input here, we say output. Okay, so output reference, source, output reference index, output reference. Cool, and then we put we don't put this into SSAs. I don't think. We put it in the reference value. So we actually want like reference pointer here, and we want to get like the pointer to that thing. And we say reference pointer is equal to the input. There we go. That makes sense. That makes sense. So now at the very end, if we just try to store that thing, we should see at the very end that we have outputs at 0 should equal to this thing that we constructed with our move command. 264. He says input doesn't exist in store. That's true. That is true. Oh, let's fucking go, dude. Let's go. Okay, so now we just need to hook this up into Mesa. So we'll kind of say like implement our GPU instruction set, right? And now all we have to do is hook it up to Mesa. So we'll say hook up to Mesa. I'm not going to pipe it all the way through to the QEMU GPU for now, because I don't think that that's going to be doable in a short amount of time. But I think that we should be able to get, at the very least, this working with Mesa. So we need to like export these functions in a way that Mesa can use them, right? So we've kind of made this like very ziggy, right? We have like push command, push input, push output. This make var is not used, right? Yeah, get this fucking shit out of there. So we're going to have to do something that's like lib GPU create shader. Which I guess will create like a struct lib GPU shader, right? And then we're gonna have like a function that's, we need to like a way to like construct essentially each of the commands that we can use, right? So we're gonna be like lib GPU push command load ref, right? And he's gonna take in our lib GPU shader as well as the ID. And the reference type. How do we do this? How do we do this? This is not trivial. Okay, actually, I think we call it there, because I think this is going to actually be a non-trivial amount of work, because we have to like map all of our like zig types that are like these like enums to C types that can get out here. And I need to think about how I want to do that. It would be nice if we could auto-generate that stuff, right? So I'm gonna think about if there's some sort of like fancy reflection that we can do to get that for free. That'd be kind of cool. And I think that we actually have like a really fucking sick ending point here. We haven't actually like implemented everything. We haven't hooked it up end to end. But I think that we have like at the very least like some form of instruction format that we can like use, right? We still have to like binarize this thing, right? We have to like take the input and convert it into something that we can like ship over a wire over the PCI bus to our GPU. We need to be able to actually construct this thing through a C API. So there's a lot of work to do on this still, but I think that we've like at least understood the Mesa format well enough. We've walked the Mesa format a little bit in our like GPU shader creation. So the next steps here are going to be to take this shader, basically like run this set of commands that like push the commands into the shader. Then we're gonna have to have some sort of like compile step that spits it out into a binary format. Then we'll upload it to the GPU. Then we will like kind of run this execute thing on the other side from QEMU. But yeah, that's a lot of work. So I think we call it there. We had really good progress today. Really good progress. I'm actually like really fucking shocked. Or shocked, is that the right word? Stoked? Stoked seems more right. But this is like very, very, very exciting. I know that like all we got was a unit test that doesn't crash, but it's like fucking sick that it works, dude. It's fucking sick. So thank you for watching, guys. If you like what you saw, we stream most days at around 12:30 Pacific time to 4 o'clock Pacific time. It is 4:20 now, so anywhere between 3.5, or I guess almost 4 hours ago and now is when you would expect to see us. We are working on this like long-term project of trying to make a GPU. Of course, we're not actually probably going to get to that point. We're probably going to get to the point where we've made a full virtual GPU, but there's a lot more stuff to go through there. But if you want to check out other stuff that we worked on, there's a lot of playlists in here if you want to check it out. There's a GitHub link in the Twitch description. If you want to see source code for this later, it will be under GPU testing env eventually. Yeah, I think that's kind of it. There's a Discord link in the Twitch description if you want to talk about shit while we're offline. And yeah, swing back by tomorrow if you want to see more. Otherwise, I hope you had a good time. YouTube, goodbye, and Twitch, let's find someone to raid.